And you also worked under Stephen Hawking.
Mm.
So did working under Stephen have any influence on causal sets? Not on your interest in quantum gravity, which I assume it did, but on causal sets in particular?
Well, that's a super interesting question. So it's almost as if my scientific progression is Stephen's, but in time, sort of in time reversed. So
okay, explain.
So it turns out Stephen's a lot of Stephen's early work was on the causal structure of space-time. So his early work was using the sorts of techniques that Roger Penrose had devised for studying the structure of space-time and predicting essentially that singularities must form inside the horizon of black holes. Stephen used that, and he predicted that there must be a singularity at the beginning of the universe at the Big Bang. So he was one of the pioneers of what you might call global causal analysis. And in particular, he proved a really important theorem, which is if you know the causal structure of space-time, that is, if you know what events in space-time can causally affect what other events, if you have all that information, then you can deduce from just that information alone, you can deduce what's called the differentiable structure of space-time. It's essentially how smooth the space-time is. And once you know that, then you have in your hand the ability to deduce almost all of the geometrical and metrical information. So he proved a theorem which is somehow, well, we'll get on to causal sets, but that it's a key theorem in our approach to the problem of quantum gravity, which puts causal structure at the center.
Right, and you gave it a moniker, a large moniker. It had 4 names with dashes in between them. What is that?
Yeah. So it's a theorem, well, it's a concatenation of several results over a few years. So the names are Cronheimer, Penrose, Hawking, and Malamud. So Cronheimer and Penrose, because they wrote an amazing paper early on, which shows that if you know the causal structure, then you know the chronological structure. There's a slight sort of a distinction there between what events can influence what other events, just full stop.
Sure.
And what events can influence what other events just by sending a massive particle from one to the other. So the signal has to be what people call a time-like signal. Something slower than the speed of light. So those are 2 slight distinctions in this idea of causal structure. So Cronheimer and Penrose showed that if you know the causal structure, which is just what can influence what, then you actually know the chronological structure, which is what can influence what by sending a massive particle. Yeah, massively. And then that is, you can show that tells you the topology of space-time. And that's a result by Penrose. So Penrose gets in there several times in the theorem. So it could be Cronheimer, Penrose. Okay,
sure.
Anyway, so you know the topology, then Stephen showed you then know the differentiable structure, and then David Malamud put the final, he made the theorem as tight as it can be. So he showed what he deduced, he proved what the absolutely minimal amount of information you need in order to prove this theorem. What's the minimal conditions under which the weakest conditions under which this theorem holds. And then if you have all of that, the causal structure, then that theorem tells you that the causal structure of space-time will give you all of the geometry apart from one thing, and that one thing is local scale. So it tells you the geometry of space-time, except for one thing, and it just doesn't tell you what local scale is. So what the time duration is along some particular world line. It doesn't tell you that.
Okay. And then this leads to causal sets.
It's one of you might call it the theorem. It's the theorem which gives us hope that causal structure can be the underpinning for a deeper theory, a deeper understanding of space-time, sort of deeper than general relativity. I haven't finished the story about Stephen and me.
Oh, okay, great. Please continue.
Yeah. So the second thing that Stephen influenced me very much with was his adherence to the path integral approach to quantum theory as the basis for a theory of quantum gravity.
Uh-huh.
And I think that too. Later in life, Stephen became convinced that the fundamental structure of space-time was not Lorentzian. So the Lorentzian structure just basically means that causal structure, that there's light and it.
It's that minus that people see in the mixed signature. Yeah.
Yes. Yeah. So it's all the diagrams you see.
Without that, you don't have light cones.
Right. So in a Euclidean space-time, there is no distinction between time-like directions and space-like directions. They're all the same. And Stephen thought that the fundamental degrees of freedom of quantum gravity should be Euclidean spacetimes, and that the Lorentzianness of GR would emerge at some effective level. So when I started as a PhD student with Stephen, he had taken up this point of view, and I worked on a project within that approach, within the Euclidean approach to quantum gravity. So I was born as a scientist doing Euclidean quantum gravity.
Mm-hmm.
But now I've gone backwards to believing that it's Lorentzian spacetimes and Lorentzian structure and causal structure which is the most fundamental. So I went back to Stephen's early days when he was a pioneer of global causal analysis. So, but he totally influences me still. I mean, his theorem, that early theorem, and also his championing of the path integral approach is something which I learned from him, and I adhere to today.
So what's responsible for that shift that Wick rotated you from the Euclidean mindset to the Lorentzian one?
Various things. I think the Euclidean approach, it's very creative, but it didn't satisfy me enough in terms of its conceptual basis. It seemed to me in the end that also it has technical problems, but probably that one can always overcome a technical issue.
Okay.
But the conceptual issues were more, they gave me more pause, I think, which is to try to understand what's really going on. And I didn't see how you could make headway with that in a Euclidean framework where nothing happens. I mean, there's no time. And the struggle that one would have to recover any kind of concept of time, the passage of time, causality, one thing being in the past and another thing being, events being causally ordered. I totally struggled to see how one could make any headway with understanding how those things might arise in a Euclidean theory. So that it was very gradual. I mean, these things don't. Well, of course, sometimes you have an epiphany, but for me, it was very gradual.
If you enjoyed this toe clipping, then the full video is linked in the description. You should also sign up for Toe Mail, which is again in the description and the pinned comment. You'll receive immediate access to all exclusive updates from the Theories of Everything podcast. It also helps me communicate directly with the core toe community. You'll also receive my top 10 toes. Think of it as the intellectual version of Quentin Tarantino's Obsession.